As Sebastian said, my name is Aoife, and I just finished my first year as a PhD student with Professor Lucy Powell's group at CU Boulder. And today I'm presenting the preliminary analysis and problem formulation for my current project, which is an auto-tuning procedure for robust wind turbine individual pitch control. So first I want to give some background. The blade pitch angle of a wind turbine refers to the angle between the blade chord, this line here, and the plane of rotation, this line here. Varying this angle varies the angle of attack of the airfoil, thus changing the aerodynamic torque experienced by the blade. And we can use pitch, this actuation or variation of the pitch angle in a few different ways. One is collective pitch control, which involves providing all three blades with identical blade pitch commands, and it's used to track a given rotor rotational speed. So ideally, we want to maximize the power that a wind turbine harvests for a given wind speed below rated wind speed and hold it constant above rated wind speed. And we do this by increasing the blade pitch from its minimum value below rated and to track the optimal tip speed ratio, which is the ratio between the speed at which the blade tip is moving and the wind speed. And then we increase it gradually above rated wind speed to hold the rotor speed constant. And this plot here shows how the power coefficient, which is this term here in the power equation, varies with both the tip speed ratio, which will vary with the wind, and also with the blade pitch angle. So the optimum is here, but we're forced to deviate from the optimum when we want to hold it constant. So what's the issue I'm hoping to tackle? Well, wind turbines like this one here are getting larger and more flexible. And you can see the purpose of this video is to show how much these blades bend when they're rotating. So as a result of larger, more flexible turbines, they experience asymmetric loading across the rotor and tower. The most significant of these loads are the 1P or once per revolution loads. In this project, our large wind turbine of choice or model of choice is the SOAR V2F, which is a 3-bladed 25 megawatt turbine design. So it's really quite big. One of many iterations developed by a multidisciplinary team, including NREL and my own group here at CU Boulder. And in this video, you see the Sumer D, which is a 2-bladed scaled down version of a 13 megawatt design. And the loading caused by these flexible blades, and it's made flexible to use less material to reduce the cost, is precisely the loading we hope to mitigate. So wind turbines are complex, high-order coupled systems operating in a very uncertain environment, which demands more sophisticated and robust control methods than the traditional PI controllers, for example. And we are considering H-infinity control. And the postdoc I work with, Manuel, is adamant that to completely understand H-infinity control, you need a PhD. So that's what he did, but that doesn't make H-infinity very useful or accessible for new wind turbine designs and for most people like myself who wish to develop controllers for them. Particularly in the context of control co-design, which my group works with a lot, in which we iteratively optimize both the aerodynamical design of the rotor, the structural design of the blades, and the controller in parallel rather than one after another. There's a need to efficiently auto-tune such a sophisticated controller for each new turbine design, ideally in an automated way. So how can we mitigate these asymmetric loads? Well, with individual pitch control, each blade receives an additional distinct signal, which is superimposed onto the collective blade pitch signal that I discussed earlier. The basic structure of this controller is given here, where we take as input these asymmetric loads you hope to mitigate. We plug that into some filters, which then is transferred over to a PI controller, which outputs the individual pitch control commands, which is then passed on to the wind turbine. And so the loop continues. So what kind of wind conditions will induce these 1P loads, or once per revolution? Well, firstly, wind shear, or the variation of wind speed with distance from the ground, which will be significant for larger turbines across the rotor area. Secondly, tower shadow, where the effective wind speed incident on a blade is reduced as it passes the tower. Thirdly, yaw misalignment, whereby the turbine is intentionally rotated about a vertical axis to influence the wake it generates. Fourthly, turbulence in the wind. And finally, really any non-uniform wind which introduces a yawing, this motion, or tilting motion, this motion here on the rotor. So after considering the design driving cases, one of the first questions I wanted to answer was that of separability, or in other words, does the individual control of blade 1 only impact the loads along blade 1? If it did, it would greatly simplify the auto-tuning procedure. So here we have a non-linear simulation where I've varied the first blade pitch after the system has reached steady state, as you can see from these oscillations here. And I've left the others constant. As you can see, the root out of blade bending moments, which are a particular loading we care about, and the deflections, the out of plane deflections of all 3 blades are impacted. Sure, it's mostly for blade 1, but the others are also influenced. So in terms of blade coordinates, at least, no, the problem is not separable, unfortunately. In any case, in addition to these blade loadings, we also have tower and nacelle and shaft loadings to consider, which cannot be separated by blade. Here we have the frequency response of the linearized system, which has been transformed from the rotating frame of reference, or in other words, in terms of blades 1, 2, 3, to the non-rating or CDQ coordinates via this multi-blade coordinate transformation matrix. You can think of DQ coordinates as the tilting and yawing coordinates, or as the cosine and sine components of any quantity which depends on the position of the blade, such as the loading of each on each blade, for example, or that deflection of each blade. C refers to collective, or the mean value over all 3 blades. As you can see here, the gain is greatest from the blade pitch C component to the root blade bending moment C component, and similarly from D to D and Q to Q. But there is a non-zero gain on the off-diagonal components as well, as we'll see next. So my point here is that it's not completely separable, and there is a coupling here, and that coupling will actually be exacerbated for higher frequencies and will vary across different wind speeds too. So that is something that should be considered, and it is typically neglected in traditional IPC controllers. The second question I was interested in investigating was what other wind turbine outputs would be influenced by individual blade pitch control. Knowing this is crucial to formulating objective functions and constraints for the auto-tuning procedure. So using this linearized MBC transformed model for each wind speed, I measured the H2 norm, which you can think of as the area under the frequency response plot, and the H infinity norm, that's the second row here, where H2 is first. The H infinity norm corresponds to the peak value in the frequency response of the transfer functions from the D on the left and Q on the right, blade pitch commands to all other outputs. And here I've plotted those with the greatest response and left out the negligible ones. So we can see here that the generator speed on the left here, in plane blade deflections and shaft bending moments seem to experience particularly significant changes in response to individual pitch control, and should thus be considered in our objective functions and constraints. The basic structure of the individual pitch controller is given here. The out of plane blade root bending moments are MBC transformed into the non-rotating frame of reference, and the higher frequency load components, which we are less concerned about, are filtered out. These signals are then fed into a proportional integral controller, which outputs the appropriate blade pitch signal in the DQ coordinates, which we then transform back to blade coordinates and feed into the wind turbine system. So why H infinity control? Well, H infinity control involves minimizing the H infinity norm of sensitivity functions of choice. So some of the good reasons for implementing this include its robustness properties, its applicability to multi-input, multi-output systems, such as wind turbines, or realistic ones at least, and higher order models, and the way that it allows us to directly shape the frequency response of specific transfer functions. This is a bird's eye view of the H infinity control system, where we have the plant, in our case, the linearized MBC transform turbine, which will be parameter varying with the wind speed for our case. The tunable controller here. In our case, this is a series of filters to filter out higher frequency loads, and also a block PI controller or proportional integral. The inputs and outputs, where performance is measured by the induced L2 norm, that's this part here, from the inputs D to the outputs E. And we get to choose these inputs and outputs, which is what I mean by directly shaping the transfer functions or the frequency response. We also have weighting matrices or filters, which describe how the involved sensitivity functions contribute to the performance criteria. So for example, the weighting matrix W1 here could filter the inputs D1 we care about. For example, if we only care about the lower frequency components of D1. And WU could transform the output to a value appropriate for performance measurement. For example, it could scale or normalize the output. For our purposes, E could represent, for example, the rate of blade pitch change, or the deviation of the rotor speed from the reference value, as metrics that we want to control or measure. And D could measure system states, inputs, and disturbances such as the rotor speed, blade root bending moments, and blade pitch values. The tuning goals relate to our objectives. We want our transfer function to be robustly stable and to have a given stability margin, and also to track a given reference. So for example, we want ideally the blade root bending moments to track a reference of 0, as unrealistic as that may be. Ultimately, in this project, we want to develop a robust auto-tuning procedure for robust H infinity controllers, meaning that we want the auto-tuning procedure to be reliable to errors in our wind turbine models, and also errors in our specifications, that it should still tune a decent or good enough controller despite these errors. And this controller should be scheduled for different effective wind speeds, and ideally require really a minimum number of tunable parameters. And this will be the next phase of our project, to figure out what these minimum number of parameters are, and also to consider the best auto-tuning procedure to implement. So to bring all of this H infinity theory back to our application of individual pitch control, we are using the SOAR V2F 25 megawatt wind turbine model, as I mentioned, and we're currently testing H infinity controllers for this model using the MATLAB SysTune interface. Once we have gathered our learnings from this manual tuning process, we then hope to develop an auto-tuning procedure using probably one of these methods, where 0th order gradient method would be more applicable to online tuning, and particle swarm optimization or minimization of a neural net learned fatigue function will be more applicable to offline applications. Finally, we would like to then verify these tuned controllers using design driving wind fields, namely DLC 1.3, which is an extreme turbulence model. So some open questions that remain and that I'm working on investigating at the moment are how significant this DQ coupling is, because traditional IPC controllers have two PI controllers, one for the D component and one for the Q, and neglect the coupling between them. So I'd like to consider how important it is to consider this coupling. I'd also like to look at whether it would be appropriate to consider higher order 3P and 6P loads, which up to now have been filtered out, except for some literature I've seen where they've considered 3P loads. I'd also like to look at whether there is a greater need for offline or online auto-tuning, particularly in industry, and how best to formulate these tuning goals, which particular auto-tuning procedure to use, and also to investigate what could be learned from a grid-based parameter sweep of a range of controller gains, which could quite easily be conducted in WISE, which is an NREL-based optimization toolbox for wind turbines. Thank you for your attention. I'm open to